Cosmology Supplement 9, Calculating Horizon Distance with Cosmic Inflation. Hello, welcome to this supplement on calculating horizon distance with cosmic inflation for the Expansion of the Universe course. The lecture script is available at a link given in the description of this video. We covered cosmic inflation in section 23. In this supplemental video, we will calculate the cosmic particle horizon distance for the present, at CMB last scattering, and at 1 second after the Big Bang, when neutrinos decoupled from electrons. First, we will do the calculations without cosmic inflation, then we will add inflation. Consider radiation that is emitted at some other distant location at time t sub e in the past, streams freely through the expanding universe at the speed of light, and arrives at our location at time t sub d, subscript d for detection time. The co-moving distance r between those 2 points, the emission point and the detection point, is this integral, where a of t is the scale factor function of time, and c is the speed of light. If the term co-moving distance is unfamiliar to you, and perhaps starting to make you anxious, think of this as the unscaled horizon distance, as we will see. The two times determine the co-moving distance. If we change either time, we change the co-moving distance. We keep our location where the radiation arrives and is detected. If we consider a specific direction and we change either time, we change the location where the radiation was emitted that will later arrive at our location. In this video, we will be concerned with 4 times. Now, CMB last scattering, 370,000 years after the Big Bang. 1 second after the Big Bang, when neutrinos decoupled from electrons, and our assumed ending of cosmic inflation, 10 to the minus 34 seconds after the Big Bang. In this video, whenever I give a time after the Big Bang, I always mean after the Big Bang or Planck time, but I will refrain from repeating this. I have calculated the scale factor for the standard cosmological model without cosmic inflation. Using that scale factor, I calculated the integral without inflation, starting at 0 time, the Big Bang. Actually, I started at the Planck time, but that does not change any values in this video. This table gives the values of the scale factor and the integral without inflation in megaparsecs at those 4 detection times. Without inflation, at early times when expansion was dominated by radiation, the scale factor was proportional to the square root of time. Look at the scale factors for 10 to the minus 34 seconds and 1 second. Time increased by a factor of 10 to the 34, and scale factor increased by a factor of 10 to the 17, 17 being half of 34. The co-moving distance also increased by a factor of 10 to the 17th. If you like, you can do the integral and verify these numbers, but we won't do it in this video. The 4th column of the table is the cosmic particle horizon distance at that detection time. This is the product of the scale factor at that time with the co-moving distance at that detection time, with emission at the Planck time or time zero. Assuming no inflation, the present cosmic particle horizon distance in this table is 14,164 megaparsecs. You will see slightly different values in different books and articles. That is not important for this video. Differences come from using a different value for the present Hubble constant or the present energy densities. The cosmic particle horizon distance was 0.257 megaparsecs at CMB last scattering and 1.94 by 10 to the minus 14 at 1 second after the Big Bang. Notice that the cosmic particle horizon distance for 1 second was 10 to the 34 times the value for 10 to the minus 34 seconds after the Big Bang. Next, we calculate the present visible horizon distance of the cosmic microwave background. This is the present distance, the proper distance, from us to the points that emitted the CMB radiation that we receive now. First, we want the co-moving distance from CMB last scattering to now. We can use the values in the table. We start with the present co-moving distance from time zero, 14,164 in the table. We subtract the last scattering co-moving distance, 281 megaparsecs. We get 14,164 megaparsecs minus 281 megaparsecs equals 13,883 megaparsecs. Co-moving distance. Then we multiply by the present scale factor, which is 1. So we get 13,883 megaparsecs for the present visible horizon distance for CMB radiation. Now, we want to scale that present visible horizon distance to the CMB last scattering time. We take 13,883 megaparsecs times the CMB last scattering scale factor, and we get 12.7 megaparsecs at CMB last scattering. Notice that this is larger than the cosmic particle horizon distance, 0.257 megaparsecs at CMB last scattering, 50 times larger. It turns out that 2 points in opposite directions of the sky, from which we are presently receiving CMB light, could not have been in causal contact at any time before last scattering, assuming no cosmic inflation. So, why would their CMB temperatures be the same? This is the horizon problem we covered in section 23. It seems like our cosmic particle horizon distance at CMB last scattering, here, is about 50 times too small for causal contact. In this diagram, the large dotted circle represents our present CMB visible universe scaled with the scale factor for last scattering at 370,000 years after the Big Bang. 12.7 megaparsec radius, 25.4 megaparsecs diameter. It is not the size of the visible universe at the last scattering time, which is 0 because the CMB was just starting to travel. The cosmic particle horizon distance at the time of last scattering is shown here as the radius of the 5 small colored circles, 0.257 megaparsecs. we need the horizon distance at the time of last scattering to have been at least 50 times larger for the opposite points, orange and purple, red and green, to have been within our observable universe, the blue circle, at the time of last scattering. So they were causally connected in the early universe and reached thermal equilibrium in the early universe, if somehow that could be. Now let's check at 1 second, when neutrinos decoupled from electrons. Next, we calculate the present neutrino horizon distance since 1 second after the Big Bang. We take the present co-moving distance, 14,164, subtract the co-moving distance from 1 second, 9.51 by 10 to the minus fifth, to get 14,164 megaparsecs co-moving distance. Then we multiply by the present scale factor, which is 1, so we get 14,164 megaparsecs for the present neutrino horizon distance, negligibly different from the present cosmic particle horizon distance, assuming no inflation. We multiply the scale factor at 1 second, 2 by 10 to the minus 10, times the present neutrino horizon distance with no inflation, and we get 2.9 by 10 to the minus 6 megaparsecs for the scaled neutrino horizon distance. The cosmic particle horizon distance at 1 second was 1.94 by 10 to the minus 14 with no inflation. It seems like, without inflation, our cosmic particle horizon distance at 1 second is about 150 million times too small for causal contact for the cosmic relic neutrino temperature to be equal in all directions, if astronomers in coming decades should find that to be the case. Cosmic inflation. Now we want to see what effect cosmic inflation would have. Let's assume a simple case of 26 orders of magnitude of cosmic inflation, starting after 10 to the minus 36 seconds and ending at 10 to the minus 34 seconds. The present scale factor must still be 1 by definition. Scale factors for times after the cosmic inflation ending time remain the same. Scale factors for times prior to the cosmic inflation ending time get reduced by cosmic inflation. For times before the cosmic inflation starting time, the scale factor gets reduced by a factor of our assumed inflation amount, 10 to the 26th. The scale factor is in the denominator of the integrand of the integral for co-moving distance and for the cosmic particle horizon distance. Cosmic inflation reduces the denominator, which increases the integrand and the integral. Assuming cosmic inflation, the integral for times before the start of inflation increases by a factor of 10 to the 26th. For this video, I don't want to work through the math of the integral for the period between start and end of inflation. For this video, it will suffice to assume that the effect of cosmic inflation is to increase the co-moving distance for 10 to the minus 34 seconds from 9.51 by 10 to the minus 22 megaparsecs without inflation to 10 to the 26 times larger, 95,103 megaparsecs with inflation. Now we want to calculate the new co-moving distances and horizon distances with this amount of cosmic inflation. First, we separate the co-moving distance into the sum of two co-moving distances. before and after the inflation ending time. Now, we put in the inflation value for the co-moving distance for 10 to the minus 34 seconds. 95,103 megaparsecs. So this is now the co-moving distance with inflation. In our table without inflation, the co-moving distance for 10 to the minus 34 seconds was at least 17 orders of magnitude smaller than the other co-moving distances, so a negligible contribution. So, we can get the co-moving distances with inflation by adding 95,103 megaparsecs to the original co-moving distances without inflation. The co-moving distances with cosmic inflation are larger than without inflation, as are the horizon distances when we multiply by the scale factors. The final column is the ratio of the inflated cosmic particle horizon distance to the uninflated cosmic particle horizon distance from the earlier table. The present cosmic particle horizon distance gets increased by a factor of 7.7 from cosmic inflation of 26 orders of magnitude. It goes from 14,164 megaparsecs to 109,267 megaparsecs. The cosmic particle horizon distance at CMB last scattering has increased by a factor of 340, from 0.257 megaparsecs to 87.4 megaparsecs. We needed to increase that horizon distance by at least the factor of 100, and we see that 26 orders of magnitude of cosmic inflation accomplishes that. Opposite points on the last scattering surface would have been in causal contact prior to inflation, when we assume 26 orders of magnitude of cosmic inflation. So this dotted circle is the same as in our previous diagram, but all of the cosmic particle horizon distances have gotten much larger. The blue circle is the cosmic particle horizon from ourselves in the center, and all those four distant points at last scattering are now within our cosmic particle horizon at last scattering. And also, all of the points are within one another's cosmic particle horizon. You should think about the present visible horizon distance of the cosmic microwave background, assuming inflation, and assure yourself that it has not changed due to cosmic inflation. Now, let's redo the calculations for the neutrinos at 1 second after the Big Bang. Next, we calculate the present neutrino horizon distance since 1 second after the Big Bang with inflation. We take the present co-moving distance, 109,267, subtract the co-moving distance from 1 second, 95,103, to get 14,164 megaparsecs co-moving distance. Then we multiply by the present scale factor, which is 1. So we get 14,164 megaparsecs for the present neutrino horizon distance, the same as with no inflation, because neutrinos decoupled after cosmic inflation. So the calculation of the scaled neutrino horizon distance is unchanged, 2.9 by 10 to the minus 6 megaparsecs. The cosmic particle horizon distance at 1 second was 1.94 by 10 to the minus 5th with inflation. Now our cosmic particle horizon at 1 second is about 6.7 times larger than the scaled neutrino horizon distance, large enough for causal contact for the cosmic relic neutrinos, and neutrino temperature could be equal in all directions. Horizon distance versus time. How do the CMB visible horizon distance and cosmic particle horizon distance change with time? You might feel that they get closer to one another over time, but this is wrong. Let's see why. Here is a table of relevant numbers. I have checked this, but not as thoroughly as I normally would before publishing. We consider times after CMB last scattering, after 370,000 years after the Big Bang. So, I'm considering different times in different rows. The time when redshift Z was 1,000, 1 million years after the Big Bang, 8 million years after the Big Bang. Redshift Z of 50 for stars. The A-scale inflection between matter and dark energy when expansion began to accelerate. Now, the time in the future when matter will be 1% of the dark energy density, and a time in the big chill future when the scale factor reaches 100 million. The CMP visible horizon distance, this column, is always smaller than the cosmic particle horizon distance. The visible horizon distance started at 0 at the last scattering time, but the particle horizon distance had a positive value then. Both increase with time. These are all scaled distances, and the scale factor increases with time. These two columns are without inflation, and these two columns are with 26 orders of magnitude of inflation. This column is the scaled particle horizon without inflation. This column is the ratio of the visible horizon distance to the scaled particle horizon without inflation. This column is the scaled particle horizon with inflation, and this column is the ratio of the visible horizon distance to the scaled particle horizon distance with inflation. The ratio of visible horizon distance to particle horizon distance starts at 0 at CMB last scattering, and it increases with time. With no inflation, the ratio tends toward 1 at infinite time. It would be 0.98 today if there had been no inflation. With 26 orders of magnitude of cosmic inflation, the ratio is only 0.127 now, and is only increasing slowly with future exponential expansion. The unscaled comoving distances for cosmic particle horizon and CMB visible horizon increment by the same amount for a given time interval, but it's the scaled distances that we generally use. The scaled cosmic particle horizon distance minus the scaled visible horizon distance increases with time for both inflation and no inflation. So avoid saying that the visible horizon is getting closer to the particle horizon, or the size of the visible universe is approaching the size of the observable universe. But the ratios behave as I described above. I hope this video has been useful to you.